In this section 10.3, we want to just briefly look at Einstein's theory of general relativity, which turned out to be a theory of gravity. That's because this chapter we're on, chapter 10, concerns gravity, so we at least ought to mention this other theory. Einstein's theory of general relativity is a theory of gravity which has been proven to be correct. And that was done soon after he came out with the theory in 1916. What is this theory and how is it different? Well, it's very revolutionary because what he showed that even pure energy or light is attracted to another mass. Now you recall the gravitational force of Newton said that it's G times m1 times m2 divided by the distance between them squared, ignoring for a moment the sign and the vector nature. That means if you had something that had no mass, it would experience no gravitational force, according to Newton. And Einstein studied this and he came to the conclusion that gravity was a curvature of space and time. And if we think of space and time as three-dimensional space, x, y, z, and of course we can't draw that fourth dimension of time, but since we know that the dimension of a space is the number of numbers you need to specify a point, we know that in space-time, for an event, we need to specify x, y, and z, and when that event occurred. So events occur in a four-dimensional space-time. And he was able to show that that was actually warped and not Euclidean. And I'm going to show you in a minute how he arrived at that. If we think about black holes, this is a situation where the space is so warped at this point that even light could not escape. And in fact, on the surface, time actually begins to stand still. There's evidence that space is curved with acceleration, such as a rotating platform. And so let's look at a rotating platform. And I'm going to have to jump ahead and assume some things from our chapter on special relativity next semester. Many of you may already know that if we have an object that moves by us at some velocity v, then the length of that object actually is shorter. If you photograph it, it will appear much shorter than it is. And the shortening of the object is given by length that you see or photograph is the original length times the square root of 1 minus v squared over c squared. This is very, very small until I get to about 1/10 of the speed of light. And at that point, 1/10 you can see becomes that's v over squared over c squared. So v over c is 1/10. This becomes about 1/100th, or this would become 0.99, and the square root of that would begin to be something tiny, but something that could be noticed. However, at the speed of light, c, this becomes c over c, very nonlinear, and this becomes 1 squared, or 1. 1 minus 1 is 0, and the length shrinks down to 0. So even though this doesn't occur at ordinary speeds, it becomes enormous at those speeds. Time likewise changes. It changes so that the natural period between two events is given by the time interval t naught, divided by 1 minus v squared over c squared. So it's just the opposite. Rather than getting smaller, it gets much longer. So time stretches out. Now, how did Einstein take his special theory of relativity with these two equations and begin to see that space and time were warped? First of all, take a rotating platform. If we imagine a platform that rotates, could be like a merry-go-round, there's a radius r, and here we're moving with a velocity v. Now what I want you to imagine is that we get a higher and higher angular velocity omega, so that this v becomes extremely large. In fact, it approaches the speed of light. Then as we begin to walk out on this platform, what is the distance around this circle? The answer is the circumference is 2 pi r. Well, that's true, but if we start moving at a velocity v, then we have this contraction of the length, the circumference, in the direction of motion. That means actually this thing is multiplied, the circumference is multiplied by the square root of 1 minus v squared over c squared. Now, at ordinary speeds, until we get to a position on this that's moving almost to the speed of light, this is negligible. So we can still say the circumference is 2 pi r. But really, at some point when we get out there, the circumference gets larger, 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 because r does. Then all of a sudden, this term begins to take over, and it gets smaller and smaller and smaller, until finally, at the speed of light, even though this may be huge, it turns out that this becomes 0. So the distance around the circle is 0. This is obviously not regular Euclidean geometry, but something very different. Time also, events out here. If we had people sitting out here and they were corresponding with people in the inner part of the circle, their heartbeats would be very, very slow. They'd be slowed down to this extent. In fact, right out here at the edge of the circumference, where v was almost equal to c, it would turn out that time almost stopped. Once Einstein realized that time became almost standstill out here, and the distance around the circumference became approximately 0, he realized that this was not a flat space-time, but a curved space and time. Our 4 dimensions were curved, both in space and in time. Well, how did this relate to gravity? It related to gravity in the following very interesting way. He imagined another thought experiment, or as it's called in German, a Gedanken experiment. He said, in this experiment, I want to imagine that we have an elevator. And this is very typically the way Einstein thought. And on the top of this elevator, there's a hook, and we're in empty space here, perhaps, or we might be on the surface of the planet Earth. Now, if we're sitting here on Earth and I do experiments on the inside, I feel an acceleration due to gravity, g, downward. That means if I throw objects across here parallel, objects will move downward in a parallel path. But since light is not affected by gravity, light would go straight across if this is the Earth and this is gravity. But now let's contrast that with an elevator or box that's being pulled. I probably shouldn't put the hook there. It's being pulled up with an acceleration g. The question is, there's no gravity here. Can you tell the difference? Well, it turns out that matter would again bend downward, exactly because the elevator is accelerating with acceleration g. It would appear that any object, as it moved across, would accelerate downward with acceleration g. However, in this situation, light also is bent downward. So it appears that the light is attracted to the bottom, and we could tell a difference in our experiments, not between any matter whatsoever. The matter would be the same in the gravitational field or in the accelerated field, where the acceleration is the acceleration due to gravity. So with all matter, you couldn't tell the difference. They both would feel the same. But with light, you could distinguish. And Einstein then made the observation, well, it doesn't matter how small the mass is. It can be smaller, 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 infinitesimal, and finally, suddenly, when the mass is 0, it would go straight across, and not in this case. It would bend in this case, and not in this case. He said, I believe they're the same. I believe that acceleration and gravitation, here we have gravitation, here we have just acceleration that's equal to g in the form of acceleration. He said, I believe they're identical. Therefore, he predicted that light would be bent, not go straight across, but be bent by gravity in exactly the same way that that same accelerated room would provide for gravity if it were accelerating. So now, what has Einstein shown? He's shown that a theory of acceleration is a theory of gravity, and a theory where we have a rotating platform is not Euclidean. So he's learned from this one that space-time is not flat. That is not Euclidean geometry, where parallel lines never meet. not Euclidean. It's not flat. And here, by this thought experiment, he's shown that what? That a theory of acceleration must be a theory of gravity. So gravitation is a theory of acceleration, and conversely. And so when he tried to generalize his special theory, and his special theory only had to do with constant velocities, when he tried to generalize it to accelerations, he realized it had to be a theory of gravity. This is how he came up with this theory. He finally was able to predict that light was bent by gravity. One of the most famous predictions that was confirmed, if we take the Earth, you can say, how on earth could we see gravity bent by, light bent by gravity? Well, you have to have some huge mass. The only thing we could think of was the sun itself. And taking a star, a source of light back here, the star was actually there, it could be bent so that the star would appear to be here, when in fact the star was over here, therefore deviating by this angle. How would we know that angle? Well, we'd know where, as the sun moved in its apparent movement across the sky, where the Earth moved around the sun, we know where this star is. And if it's really behind the sun and appears to be over here, then we can see what that deflection is. However, we can't look right at the edge of the sun and see a star. We had to wait for a lunar eclipse. And it's just fortunate that the moon is about the same angular size as the sun. And this experiment was performed in South Africa, and it verified the motion of the stars. In fact, the stars that were behind the sun, in fact, appeared to be out to the side. And that confirmed Einstein's general theory that space and time were curved, and that a theory of acceleration is a theory of gravity.